Imagine scientists confirm tomorrow that an intelligent civilization exists somewhere in this galaxy. Not a statistical argument, not a candidate signal, a confirmed contact. Repeating, structured, artificial. Every major government on Earth issues a statement by morning. The question humanity has asked since the first person looked up at the night sky is finally answered. We are not alone. Now here is the part that breaks it. The signal originates 1,000 light years away. It left its source in the year 1025. When it departed, no European had yet reached the Americas, the Crusades had not started, and every language spoken fluently on Earth today was either unrecognizable or did not exist. The signal has been crossing empty space at the speed of light for an entire millennium and has only now reached our instruments. If we reply today, our reply arrives in 3026. Their response to that reply arrives here in 4026. By then, every person alive today will have been dead for 2,000 years. That is the best case scenario. That is what contact looks like with the closest plausible neighbour. And that four-word question Fermi asked at a lunch table in 1950 stops being a puzzle and starts being something heavier once you understand what the silence actually measures. Where is everybody? If this is the kind of science that stays with you after the lights go out, subscribe before we go further. It costs nothing, it helps other people find this. Now, let's begin. You already know the basic setup. Space is vast. There are a lot of stars. Somewhere out there, statistically, there should be other life. That is not an eccentric position. That is what the arithmetic says when you apply it carefully to what we now know about the galaxy we live in. And the arithmetic is considerably more forceful than most people realize the first time they encounter it. In 1961, an astronomer named Frank Drake sat down at a conference in Greenbank, West Virginia, and wrote an equation on a blackboard. He was not attempting a definitive calculation. He was organizing a conversation among scientists who wanted to think carefully about a problem no one had a shared framework for. The equation has borne his name since. In 60 years of challenge and refinement, nothing has replaced it as the organizing structure for this question. The equation breaks the problem into a chain of factors. How many new stars form in the Milky Way per year? Of those, what fraction develop planetary systems? Of those systems, what fraction include a planet in the zone where liquid water is stable at the surface? On such planets, what fraction develop life? Of those, what fraction develop intelligent life? Of those, what fraction develop technology capable of broadcasting detectable signals? And finally, how long does such a civilization remain in a communicating state before it goes quiet? Multiply those factors together and you get an estimate of how many civilizations might be broadcasting right now. When Drake ran the calculation in 1961 with the best available estimates, the answer came out between 1,000 and 100 million. The range is large because several variables were genuinely unknown at the time, but the critical insight is that even the pessimistic lower end of that range is 1,000. 1,000 civilizations in the Milky Way actively broadcasting at this moment. The math does not whisper that life might exist out there, it screams it. Since 1961, the variables we can actually measure have come in consistently on the optimistic side. In 1990, the total number of confirmed planets outside our solar system was 0. Not a handful, 0. The first confirmed planet orbiting a sun-like star was detected in 1995. By 2018, when NASA's Kepler Space Telescope finished its primary mission, it had confirmed 2,162 exoplanets and pointed toward thousands more. The statistical analysis of Kepler's data produced a result that changed every downstream conversation about the Drake equation. On average, every star in the Milky Way has at least one planet. The galaxy is not mostly isolated suns surrounded by empty space. It is crowded with worlds. More specifically, analyses of Kepler data suggest between 300 million and 40 billion planets in the Milky Way sit in the habitable zone of their parent star and are roughly Earth-sized. Take the pessimistic end of that range, 300 million. Here is what 300 million means in a unit you can feel. If you wanted to visit every potentially habitable planet in the Milky Way and spent exactly 1 second at each before moving to the next, the trip would take over 9,500 years. You would need to have started before the Egyptian pyramids existed. That is the low estimate. Sit with that for a moment. Since Kepler, the work has continued and deepened. NASA's TESS satellite, launched in 2018, extended the exoplanet survey toward nearby bright stars where follow-up atmospheric characterization is practical. The James Webb Space Telescope, operational since 2022, carries infrared instruments capable of analyzing the light that filters through a planet's atmosphere during a transit, revealing which gases are present. Webb has already detected carbon dioxide, water vapor, and sulfur dioxide in exoplanet atmospheres. The search for oxygen and methane in biosignature combinations is underway. The inputs to the Drake equation have continued to point in the same direction. The more we measure, the more populated the equation predicts the galaxy to be. There is one variable in the Drake equation that resists measurement entirely and controls the output more than any other. It is called L, the average length of time a civilization remains in a detectable communicative state. If L is large, if civilizations broadcast for millions of years, the galaxy should be filled with overlapping signals from many directions simultaneously. If L is small, if civilizations tend to collapse or go electromagnetically quiet within a few thousand years, the population of active communicators at any given moment drops sharply. Most of what ever existed came and went long before we developed instruments to notice. The cosmos is old enough that the vast majority of this story may have played out before our sun formed. Humanity has been detectable for approximately 100 years, since commercial radio broadcasting began around 1920. Our signals have been leaking into space at the speed of light since then. A sphere of space centered on Earth, roughly 100 light-years in radius, currently contains detectable evidence that we exist. That sphere contains about 15,000 star systems. In a galaxy of 400 billion, 15,000 is not a fraction worth calculating. We have barely started talking, and the equation still predicts we should hear something. We have not. The Drake equation's prediction also changes depending on which part of the Milky Way you're in. The galactic center has a higher density of stars and a longer history of stellar formation, but it also has a higher rate of supernovae and energetic events that could sterilize nearby planets. The outer regions of the galaxy have fewer stars and a lower density of heavy elements, which might reduce the rate of rocky planet formation. The galactic habitable zone, a concept developed by astronomers Guillermo Gonzalez and James Casting, refers to the region of the Milky Way, where conditions are most favorable for complex life, roughly an annular region between 7,000 and 9,000 light-years from the galactic center. Earth sits toward the outer edge of this zone. Within the galactic habitable zone, the conditions for Earth-like planets and complex life are relatively favorable. If the habitable zone contains a smaller fraction of all the stars in the galaxy than the total might suggest, the population of candidate civilizations is correspondingly smaller. But even the most conservative estimates of the galactic habitable zone's population suggest hundreds of millions of candidate star systems, which does not change the fundamental prediction of the Drake equation by more than a few orders of magnitude in the pessimistic direction. The silence persists. Here is what 15,000 star systems means in a different unit. The Milky Way contains approximately 400 billion star systems. 15,000 is Boston's 3% of that total. If the galaxy were a country with 400 billion residents, We've introduced ourselves to about 15,000 of them. The rest have never heard of us, and yet we're asking why none of them have contacted us. We have been talking for a century, our voice has reached 15,000 potential neighbours, and we are already surprised by the silence. The scale mismatch between how long we have been broadcasting and what we expect to receive in return is part of what makes the Fermi paradox simultaneously so compelling and so difficult to resolve. There is also a specific complication in how we are listening. Our SETI searches have largely focused on the hypothesis that other civilizations would broadcast omnidirectionally, the way our early radio transmissions leaked into space in all directions simultaneously. But omnidirectional broadcasting at interstellar detectable power levels is expensive. As we advance technologically, we're moving away from omnidirectional radio toward directed communication. Within a century or two, it is plausible that Earth becomes electromagnetically quiet from the outside, not because we stopped communicating, but because our communication became more efficient and therefore less detectable at distance. If this is a common trajectory, detecting civilizations by their leakage radiation requires catching them in the specific window between developing radio technology and transitioning away from it. We are looking for a very specific phase of a civilization's development in a very specific frequency range across a very large sky. The probability of overlap between our search window and another civilization's broadcasting window may be much lower than the Drake equation's naive reading suggests. There is a refinement to the Drake equation's framework that matters for understanding the silence. The question is not only how long a civilization lives, but how long it broadcasts in ways detectable from interstellar distances. A civilization might transition from omnidirectional radio broadcasting to tightly focused laser communication or buried fiber optic infrastructure within a century or two, becoming electromagnetically invisible from the outside without ceasing to exist. If this is a common trajectory, the effective window of radio detectability is very short even for civilizations that survive indefinitely. The galaxy could be full of long-lived invisible civilizations, each having passed through a brief radio era that is now complete, with no overlap between their broadcasting windows and our current listening. This resolution is sometimes called the transcension hypothesis. It sounds satisfying until you apply it to the physical artifact problem. A civilization that has been managing stellar-scale energy for 1 billion years, even if it communicates via tight laser beams directed only at specific recipients, would have altered the energy budget of its star system in ways visible to infrared surveys, regardless of communication choice. Waste heat is waste heat. The transition away from radio does not explain the absence of megastructures. It solves one silence while leaving the deeper one untouched. The Drake equation presents a precise puzzle. The inputs consistently favour a populated galaxy. The outputs we search for consistently fail to appear, and something in the chain from star formation to broadcasting civilization is doing filtering work that the equation's optimistic inputs do not account for. The filter is not in the equation. It is what the equation's failure to predict the silence implies must exist. The 6-step explanation formula helps clarify what the Drake equation is actually measuring at each step. Take the factor that measures what fraction of habitable planets develop life. In 1961, Drake had no data for this. He estimated. Since then, our understanding of the chemistry of life has expanded considerably. But we have not resolved the fundamental question: does life arise readily whenever conditions are right? Or does it require an improbable accident? We know that amino acids form easily. We know that organic chemistry is widespread in the universe. We do not know whether the transition from organic chemistry to a self-replicating system happens quickly and reliably, or slowly and rarely. That single unknown controls the Drake equation's output by potentially many orders of magnitude in either direction. Now let us make the uncertainty more extreme. Suppose we knew that the probability of life arising on a habitable planet in a given billion-year window was exactly 1 in a million. In a galaxy with 300 million potentially habitable planets and a history of 13 billion years, that probability still produces hundreds of billions of instances of life arising across galactic history. The number of occasions life would have had to arise and develop technology would still predict a crowded galaxy. Now suppose the probability is 1 in a trillion. Then the galaxy might contain only a few hundred instances of life total. Now suppose it is 1 in 10 to the power of 20. Then the observable universe might contain only one. The range of outcomes that the single unknown variable of life's origin probability can produce spans from galaxy obviously full to Earth is alone in the observable universe. The Drake equation is not a calculator. It is a way of locating our uncertainty precisely enough to know which observations would resolve it. This is why the James Webb Space Telescope's atmospheric characterization program matters so much to the Fermi paradox. If Webb finds that biosignature gas combinations are present in the atmospheres of multiple Earth-sized planets in habitable zones around nearby stars, the probability of life arising is revealed to be high. The Drake equation's output for the current population of broadcasting civilizations then pushes strongly toward a large number. The filter's location under that scenario is forced into either the biological complexity steps or the technological survival step. The future filter scenario becomes more likely, and the silence becomes more disturbing. If Webb finds no biosignatures in the dozens of planets it characterizes, that null result supports the rare Earth interpretation and suggests the filter is early. The silence becomes less disturbing. One telescope program can shift the probability in a meaningful direction. That is a specific kind of scientific progress that was not possible before 2022. The galaxy should be answering. It has not. That is where the problem deepens. There is an implication within the Drake equation structure that rarely surfaces in popular discussions. The equation is not only about counting civilizations at this moment. It's about compounding probabilities across 13 billion years of galactic history. If star formation produced potentially habitable worlds throughout most of the Milky Way's existence, and if even a small fraction of those worlds developed intelligence, then civilizations have been arising and potentially falling for most of the galaxy's recorded history. Not just in the last billion years, potentially for 10 or 11 billion years. The silence is not the silence of a young galaxy with few opportunities. It is the silence of an ancient one with billions of them. Consider how that changes the scale of what we need to explain. It is not enough to account for the silence of the last few hundred years since we developed instruments capable of detecting a signal. We need to account for the silence of the last billion years, a civilization that arose 5 billion years ago, expanded at 1% of light speed, and built structures harvesting stellar energy should have left marks visible from thousands of light years in every direction. Those marks are not there. The Kepler Transit Catalogue, the WISE infrared survey, the radio surveys conducted across every frequency range we have examined, all return the same answer. An ordinary galaxy following ordinary physics with no sign of civilizational scale engineering anywhere. There is a secondary consideration that modifies the Drake equation's predictions in a specific direction. The hypothesis called panspermia proposes that life, or the chemical precursors to life, can be transported between planetary systems by debris ejected from large impacts. When a large asteroid strikes a planet's surface, it can accelerate rock fragments to escape velocity. Those rocks travel through space, potentially reaching neighbouring star systems over millions of years. Organisms embedded in rock fragments can survive the vacuum and radiation of interplanetary space for substantial periods in laboratory experiments. If panspermia operates between star systems, the effective number of independent origins of life in the galaxy could be much smaller than the Drake equation naively assumes. Life might propagate readily from one origin point, but arise from scratch very rarely. This would reduce the expected population of technological civilizations, while still leaving the galaxy's inhabited worlds seeded from a small number of initial events. And if those initial events produced only biological life without technological civilization, the silence would still be explained, but with a different mechanism than rarity of life altogether. The panspermia modification does not change the fundamental structure of the Fermi paradox. What it does is clarify where the filter most likely operates if life itself is not the rarity. If life can spread between worlds, and if simple microbial life is therefore relatively common, then the filter is in the later steps. The transition from simple life to complex life, from complex life to intelligence, from intelligence to technology, or from technology to long-term survival. Panspermia moves the origin of life filter into the past filter column with high confidence, which in turn means any remaining filter is in the biological complexity column or the technological survival column. The question of which of those is the bottleneck is exactly the question the discovery of life on Mars would begin to answer. Most people assume the search for signals from other civilizations is conducted at the margins of astronomy, a speculative hobby between more rigorous work. That picture has been wrong for 6 decades. In April 1960, Frank Drake pointed an 85-foot radio telescope at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, both within 12 light-years of Earth. He tuned to 1020 MHz, the frequency at which neutral hydrogen emits radio waves naturally. This frequency, known as the hydrogen line, was chosen deliberately. Hydrogen is the most common element in the universe. Any civilization with radio technology would derive its emission frequency from the same physics. If anyone wanted to be found, this was the natural channel. Drake called the project OSMA. Over roughly 150 hours of observation across several weeks, he detected nothing anomalous. That was the beginning of a search that has never stopped. The next several decades saw a proliferation of search strategies. Different teams tried different approaches. The Meta and Beta surveys at Harvard, run by Paul Horowitz, scanned millions of narrow channels simultaneously, looking for any narrowband signal above background noise. The Project Phoenix survey, run by the SETI Institute after the NASA program was cancelled, targeted 800 nearby sun-like stars with the most sensitive equipment available at the time and found nothing of interest. The southern hemisphere was covered by Project Serendip, a commensal search running on a telescope time shared with other astronomical programs. The Soviet program surveyed the full sky with a wide-beam telescope, operating on the assumption that a powerful transmitter would be detectable across large fractions of the sky simultaneously. All of these programs had different assumptions about what a signal might look like, where it might come from, and at what power level it would be broadcast. None of them produced a confirmed detection. One point worth emphasizing is how the definition of a search affects the interpretation of its results. When we say breakthrough listeners scan the nearest million stars, we mean it as look for narrowband signals above a specific power threshold within a specific frequency range in the direction of those stars using radio wavelengths. It has not searched those stars for laser pulse signals. It has not searched them for infrared anomalies. It has not searched them for modulated signals at frequencies outside the radio range. Each of those limitations is a genuine limitation on what a null result means. The null result means Among the nearest million stars, no narrowband radio signals above the detection threshold were found in the frequencies searched. That is a real and important result. It is not an exhaustive result. The universe of possible signal types, frequency ranges, and detection modalities is much larger than any single program can cover. The SETI null result should be understood as a precisely characterized boundary, not as a claim of comprehensive coverage. Over the following decades, the search expanded in every dimension. Radio telescopes became more sensitive. The frequency range scanned widened beyond the hydrogen line to cover a broader spectrum. Computer processing allowed researchers to analyze far larger data volumes for patterns that human reviewers could never practically find manually. The Soviet Union conducted parallel SETI programs throughout the 1960s and 1970s, using different designs and different strategies, and producing different null results. NASA funded a formal SETI program from 1988 until Congress terminated it in 1993 in a budget debate during which senators competed to make jokes about little green men. The termination was not a scientific judgment. The scientists reorganized into private and non-profit structures and continued. The WOW signal lasted 72 seconds. That is the loudest thing the universe has ever said to us. On August 15, 1977, the Big Ear Radio Telescope at Ohio State University was running a routine sky survey. The following day, a researcher named Jerry Eman reviewed the printed data and found something that made him circle a sequence of characters in red pen and write one word in the margin beside it. The signal was 30 times stronger than the background noise of space. It was narrowband, concentrated in a tight frequency range, which is exactly the profile deliberate transmission would carry rather than a natural astrophysical source, which typically emits across a wide range simultaneously. Its center frequency was close to 1,420 MHz, and it lasted exactly 72 seconds, which was precisely the duration the Earth's rotation allowed it to remain in the telescope's field of view. It has never been detected again. In the 47 years since that night, follow-up observations at that region of sky using multiple telescopes have produced nothing. Ohio State repointed at that location more than 50 times before the observatory was demolished for a golf course in 1997. The signal remains classified as unexplained, not confirmed as extraterrestrial, and not attributed to any natural or human-made source that has been proposed. In 2016, one researcher suggested the signal might have been caused by hydrogen clouds surrounding comets passing through the field of view. Other researchers disputed this on the grounds that the signal's bandwidth was inconsistent with comet hydrogen emission. The debate is not fully closed. The honest scientific position is that the WOW signal is still unexplained, and it has produced no follow-up. Let that settle before we go further. In 2015, Breakthrough Listen launched with $100 million in funding from entrepreneur Yuri Milner. The program uses the Greenbank Telescope in West Virginia and the Parkes Telescope in Australia for large blocks of dedicated observing time, scanning the nearest million stars, the 100 nearest galaxies, and the full galactic plane. Breakthrough Listen generates more SETI-relevant data in a single day than all previous searches combined over the prior history of the field. In 2020, it published an analysis of 1,227 nearby stars. No signals met the criteria for further consideration. In late 2020, the Parkes telescope detected a narrowband signal at 982 MHz, apparently originating from the direction of Proxima Centauri, the closest star to our Sun at 424 light-years. Proxima is known to host at least one planet in its habitable zone. A narrowband signal from that direction, at a frequency not matching any known natural astrophysical source, was precisely the kind of detection the search was designed to find. The signal was designated BLC-1. After months of careful analysis, researchers concluded in 2021 that BLC-1 was almost certainly radio frequency interference from human-made equipment near or at the observatory, a terrestrial source, another null result. There is a lot to absorb there, but radio silence is only one layer of the absence. A civilization old enough to matter to the colonization timescale, one that has been expanding for millions of years, would have reorganized energy at a scale visible across thousands of light years, regardless of what communication technology it uses. A structure capturing most of a star's energy output would cause that star to dim in visible light, while glowing anomalously bright in the infrared, because all that captured energy eventually becomes waste heat. NASA's WISE satellite conducted a complete infrared survey of the sky at a resolution and sensitivity capable of detecting such signatures around nearby stars. A team led by Jason Wright at Penn State analysed the full WISE catalogue specifically looking for these signatures. The analysis found no confirmed candidates consistent with large-scale stellar energy capture anywhere in the observable sky. In 2015, a star designated KIC 8462852, subsequently nicknamed Tabby Star, attracted significant attention when researchers reported anomalous brightness dips of up to 22% in Kepler data, irregular in shape, timing, and depth, matching no standard models for planetary or stellar phenomena. It was briefly taken seriously as a megastructure candidate. Follow-up observations across multiple wavelengths established that the dimming was wavelength-dependent in a way inconsistent with solid structures and consistent with clouds of fine dust at various orbital distances. Tabby's star is almost certainly a natural phenomenon, probably involving disrupted cometary material. But the fact that it attracted such attention reflects how seriously the search for physical artifacts of advanced civilizations is taken by researchers who work in this field. We are not missing a phone call. We are missing the footprints of something that should have been leaving marks in this neighbourhood for longer than Earth has existed. There is also the question of what the silence looks like when expressed in terms of what we should be seeing rather than what we are failing to hear. A civilization that has been harvesting stellar energy at the scale of a Kardashev Type II civilization, using the full energy output of a single star, would produce roughly 4 times 10 to the power of 26 watts of waste heat. That heat would be radiated at infrared wavelengths, producing a specific spectral signature that differs from the natural emission of the same star. At a distance of 1,000 light-years, such a signature would be detectable by the infrared instruments available today. At 10,000 light-years, it would be marginal but potentially detectable with planned next-generation instruments. The WISE analysis searched for this signature around approximately 100,000 nearby galaxies and found no confirmed candidates. The silence is not just the absence of a whisper, it is the absence of a bonfire. A Kardashev Type III civilization, one using the energy output of an entire galaxy, would produce a signature detectable across hundreds of millions of light-years. The Jason Wright Penn State analysis using WISE data searched for anomalous infrared emission in nearby galaxies, looking for the signature of galaxy-wide energy capture. Of the approximately 100,000 galaxies analysed, a subset of roughly 50 showed elevated infrared emission relative to their optical brightness. All 50 were subsequently attributed to natural astrophysical processes, primarily star formation activity heating dust in the interstellar medium. None showed the specific spectral characteristics that would distinguish galaxy-scale engineering from natural emission. The observable universe, surveyed in infrared across enormous volumes, shows no signs of civilizations operating at galactic scales. The null result from radio and infrared searches has a specific and often understated implication. The Fermi paradox is sometimes presented as though the silence could be explained by simple distance. Maybe the signals are there, but they haven't reached us yet. maybe the civilizations are too far away. This explanation only works if civilizations are absent within a specific radius of Earth. But radio signals from civilizations broadcasting at 10,000 times the power of our own strongest intentional transmissions would be detectable by current instruments across hundreds of light years. And infrared signatures of stellar-scale engineering would be detectable across thousands of light years. The silence is not limited to what is too distant to reach us. It extends through all of the space our instruments can actually see. The search for physical artifacts extends into our own solar system in ways that are often overlooked. The moon's surface is particularly relevant. It has no weather, no plate tectonics, and no atmosphere to erode or bury evidence. Anything placed on the lunar surface 1 billion years ago would in principle still be there, preserved by the moon's geological inactivity. The moon has been mapped at increasing resolution over the past several decades, first by orbital photography and then by increasingly detailed laser altimetry and radar mapping. No anomalous structures or artifacts have been identified. The absence of evidence on the lunar surface, given its exceptional preservation of ancient objects, is meaningful. It suggests that if any probe or artifact was placed in or near our solar system in the past billion years, it was not on the moon at any detectable scale. In 2017, an object designated Oumuamua became the first confirmed interstellar visitor detected passing through our solar system. Its properties attracted significant scientific attention. Its shape, inferred from the variation in its reflected brightness as it tumbled, was unusually flat and elongated, unlike any solar system object previously characterized. Its trajectory showed an acceleration component not fully explained by the gravity of the Sun or by radiation pressure acting on a typical rocky surface. The Harvard astronomer Avi Loeb proposed that it might be a light sail, a large, thin, artificial structure pushed by solar radiation as it passed through the inner solar system. This proposal received substantial public and scientific attention. The mainstream scientific response has favoured natural explanations. The most widely accepted is that Oumuamua was a shard of nitrogen ice from another planetary system, fragmenting from a body similar to Pluto. Nitrogen ice would sublimate rapidly during the close solar approach, producing the excess acceleration without generating a visible gas coma, because nitrogen molecules are difficult to detect at the relevant temperatures and distances. This explanation has its own challenges, primarily around how such an object survives the interstellar crossing without sublimating entirely. The scientific debate is not fully closed. Whether Oumuamua was artificial or natural, the encounter is instructive. It would not announce itself with a beacon. It would appear as an anomaly in observational data that requires sustained analysis and debate to characterize. The CT literature has long discussed the possibility that the first evidence of extraterrestrial intelligence might not be a directed radio message but a physical object whose artificial origin only becomes apparent after careful study. The Vera Rubin Observatory in Chile, now operational, is expected to dramatically increase the discovery rate of interstellar objects passing through our solar system. More encounters like Oumuamua will occur. They will be characterized with greater precision. Whether any of them survive careful analysis as artificial remains to be seen. Here is where most people reach for distance as the explanation. The galaxy is 100,000 light-years across. Signals take a long time to cross it. We're young. We haven't waited long enough. That is a natural first assumption. It is not where the hardest problem lives. The hardest problem is time. And once you run the colonization arithmetic, the silence becomes not just quiet, but geometrically strange. If Earth's entire history were compressed into 24 hours, here is where things fall. Life appears at 4 a.m. Complex multicellular life does not arrive until 8:30 in the evening. Modern humans appear in the last 3 seconds before midnight, and the moment we became capable of transmitting radio signals detectable from other star systems, that happens in the last millionth of a second before midnight. Our communicative window is 0.0027% of Earth's history, 3 millionths of 1%. Now apply that same timeline to the galaxy. The Milky Way is 13.6 billion years old. If the sequence from simple life to technological civilization took roughly 4 billion years on Earth, a planet that formed just 2 billion years earlier in galactic history and followed a similar timeline would have produced a technological civilization 2 billion years before ours. 2 billion years. Against what colonization timescale? A civilization that got a 10 million year head start on us should have been here before the dinosaurs fell. A civilization travelling at 1% of light speed, which is about 6,700 miles per second, roughly 56 times faster than the fastest human spacecraft ever built, could cross the full diameter of the Milky Way in 10 million years, not in a single voyage. As a propagating wave of colonization, each new outpost expanding to its own neighbouring stars, the frontier spreading outward the way fire moves through a forest from every point simultaneously. Computer models of this type of expansion consistently produce galactic saturation timescales between 5 million and 100 million years, using technology that requires no new physics. 2 billion years divided by 100 million is 20. A civilization with a 2 billion year head start would have had time to saturate the galaxy and do it again 19 more times, with time remaining before Earth's first vertebrates crawled onto land. The absence of any sign of such a civilization is not merely a gap in our radio coverage. It is an absence of physical engineering at stellar scales, an absence of anomalous infrared signatures in all sky surveys, an absence of megastructures in exoplanet transit catalogues, an absence of anything in the observable data that would indicate a billion-year-old civilization has ever operated in this galaxy. The sky is not muted, it is clean. A clean sky against that backdrop is a measurement that demands a serious answer. We have covered a lot of ground. Take a breath. The Hart-Tipler argument, formalized by astronomers Michael Hart and Frank Tipler in the 1970s and 1980s, makes the colonization case more precisely. Even without biological expansion, a civilization could launch self-replicating robotic probes that spread through the galaxy using local materials to build copies of themselves. Each probe reaching a new star system would construct several copies and send them onward. The wavefront of probes propagates faster than any manned colonization effort. At conservative assumptions, a self-replicating probe program launched 1 billion years ago should have produced probes that visited every star system in the Milky Way many times over by now. Our solar system should have been visited. Evidence of that visit, in the form of anomalous objects or structures detectable by modern surveys, should be present. Nothing unambiguously artificial has been found in our solar system in centuries of increasingly careful observation. The colonization argument and the radio silence argument are independent lines of evidence. Together, they make the Fermi paradox very difficult to dismiss. They are both pointing toward the same conclusion. Something is preventing civilizations from accumulating in the galaxy the way the mathematics predicts. That something must be nearly universal, a nearly universal filtering of civilizations at a consistent point in their development is what the Great Filter Framework describes. There is a specific and often underappreciated argument that makes the colonization silence even harder to explain away. It is not necessary to assume that an expanding civilization colonizes every star system it passes. Even a highly selective expansion, one that only targets a small fraction of suitable systems, still produces galactic saturation on timescales short compared to the galaxy's age. at 1% of light speed, colonizing 1 in 1,000 neighboring star systems at each wave still propagates across the full galaxy in under 1 billion years. The selectivity of expansion does not change the conclusion. Even the most cautious and reluctant imaginable interstellar civilization, one that expands only when absolutely necessary and at the smallest possible scale, would still have left physical marks across this galaxy in 1 billion years. We see none. The argument can also be framed as a minimum evidence threshold. We're not asking for a civilization to have colonized every star. We're asking for evidence of any civilization that expanded at any scale over any sustained period. The reorganization of even 100 star systems within a few thousand light-years of Earth would be detectable in current infrared surveys. The construction of even one megastructure around a star visible from Earth would appear in the Kepler Transit Catalogue as an anomaly no natural explanation can account for. We're not setting a high bar for evidence. We're setting a very low one, and that very low bar has not been crossed. The physicist Enrico Fermi was famous for a style of reasoning his colleagues called Fermi estimation, arriving at accurate order of magnitude answers to complex questions by careful logical decomposition from first principles without looking anything up. The piano tuners in Chicago, the weight of the Earth. He would pose these problems at lunch and work through them on a napkin. The question he asked at Los Alamos in 1950 was, in its structure, a Fermi estimation problem. He was not musing, he was calculating. And the calculation said the galaxy should not be silent. The sky said it was. Fermi recognized the gap immediately and captured it in 4 words. The gap has not closed, it has become more precisely measured, and measurement is what turns a puzzle into a problem. The colonization argument also has a version that removes the need for intentional interstellar travel entirely. Self-replicating probes, sometimes called von Neumann probes, after the mathematician who first described their theoretical properties, would arrive at a star system, use local material to build copies of themselves, and send those copies onward. The probes replicate, the wavefront propagates. No biological crew is required, no generational ship, no extraordinary longevity, just engineering that is self-sustaining and self-replicating. The timescale for galactic saturation by self-replicating probes at 1% of light speed is similar to the colonization timescale, tens to hundreds of millions of years. A civilization that launched such probes 1 billion years ago would have probes in every star system in the Milky Way many times over by now. Our solar system should have been visited. The evidence of that visit in the form of probes in stable orbits, structures on planetary surfaces, or materials with anomalous compositions indicating off-world manufacture should be present. We have surveyed the solar system with increasing thoroughness for centuries. No unambiguously artificial object has been found. The asteroid belt alone contains millions of objects. The Kuiper belt contains hundreds of thousands more. The Oort cloud contains trillions. A probe placed in the outer solar system 1 billion years ago would be extraordinarily difficult to find with current instruments, given its likely small size and the volume involved. The absence of evidence in this case is genuinely limited by our search coverage, but the Moon remains a different case. A probe placed on the lunar surface 1 billion years ago would still be there, relatively well preserved in the Moon's geologically inactive environment, and lunar mapping has been thorough enough at kilometre-scale resolution to rule out large structures. The absence on the Moon specifically is informative. Scientists have built a substantial catalogue of explanations for the silence over 75 years of serious attention. The list is long, and it covers nearly every conceivable reason the galaxy might appear empty, despite the mathematics suggesting otherwise. These explanations share a structural pattern. Each sounds plausible at first, each weakens substantially under careful examination, and each time one weakens, what remains is a harder version of the same problem. The first explanation most people reach for is called the rare earth hypothesis. Life, it proposes, is not merely uncommon, it is extraordinarily improbable. The specific combination of conditions that produced Earth and the biological sequence that followed may be so unusual that it almost never repeats. A star of the right type and age, not so massive that it exhausts its fuel in hundreds of millions of years before complex life can evolve, not so small that its habitable zone requires an orbit so close that stellar flares sterilize the surface periodically. A planet at precisely the right orbital distance for liquid water to be stable over billions of years. A large moon stabilizing axial tilt so that seasons remain within survivable ranges rather than swinging to extremes that would periodically devastate ecosystems. A gas giant in the outer solar system deflecting the majority of large impactors before they can reset the biological clock every few 100 million years. Plate tectonics cycling carbon through the atmosphere and regulating long-term temperature. Stack enough requirements, and the probability of any given star system hosting intelligent life drops towards zero. The rare earth argument is a serious scientific position, developed in technical detail by researchers, including Peter Ward and Joe Kirschvink. The challenge it faces is scale. The observable universe contains approximately 2 trillion galaxies, each with hundreds of billions of stars. Even if the probability of complex life arising in a given star system is 1 in a trillion, the expected number of complex life sites across the observable universe is measured in billions. For rare earth to explain the silence of the Milky Way, the probability per star system must be so low that our existence here is an event that should not have happened even once in the entire history of the universe. You can hold that position, but you should know what it costs. The universe is not refusing to answer. It has answered. We just don't like what the answer implies. The rare earth hypothesis has a specific empirical implication that is now testable in ways it was not when the argument was first formalized. If the conditions for complex life are genuinely unusual, we would expect that exoplanet characterization would reveal that Earth-like planets with Earth-like chemistry are rare exceptions rather than common occurrences. The James Webb Space Telescope is already beginning to produce the atmospheric data required to test this prediction. If Webb characterizes dozens of habitable zone terrestrial planets and finds that oxygen-methane biosignature combinations are absent from all of them, rare earth gains support. If even one exoplanet shows biosignature combinations consistent with life, rare earth's central claim is refuted for the origin of life step, though it could still apply to complexity or intelligence. The hypothesis is moving from an unfalsifiable philosophical position toward a testable scientific prediction. That is progress, even if the answer it produces is uncomfortable in one direction or the other. The second class of explanation addresses communication directly. Maybe civilizations exist in abundance, but communicate in ways we cannot detect. Radio waves may be a primitive technology that advanced civilizations quickly abandon. A civilization 1,000,000 years more developed than ours might use laser pulses concentrated in tight beams, directed at specific recipients, rather than broadcasting omnidirectionally. It might use modulated neutrino beams. It might use technologies with no analogue in our current physics. This concern is real, and it has driven the expansion of SETI beyond radio searches into optical SETI programs that scan for laser pulses. The expansion is scientifically appropriate. But the communication technology argument does not address the physical artifact problem. A civilization that has been expanding across the galaxy for millions of years would have reorganized matter and energy at scales visible regardless of what frequencies it uses to talk. Dyson sphere heat signatures, megastructure transit curves, anomalous infrared emissions from reorganized stellar systems. None of these depend on what channel the civilization uses to communicate. The absence of physical artifacts is a separate and independent silence from the absence of radio signals. Explaining away the radio silence does not explain away the engineering silence. Hold that for a moment before we continue. The third explanation, called the zoo hypothesis, proposes that we are in a protected reserve. Advanced civilizations know we exist and have agreed not to make contact, watching us the way a researcher might observe an isolated community without disturbing it. There is a galactic convention. Every spacefaring civilization has independently arrived at the same non-contact policy and has maintained it without a single exception. One rogue civilization breaks it. One individual within any civilization transmits without institutional approval across any point in the past billion years. One automated probe launched before the contact suppression policy was established continues to send. One faction within one civilization disagrees with the majority and acts. Any single exception, anywhere in the galaxy across all of time, breaks the silence. The zoo hypothesis requires unanimity of behavior across all sapient life, across all space and all time that exceeds anything in the human record and requires no motivation we can verify. It cannot be falsified and it cannot be confirmed. It is not a resolution. It is a story shaped like a resolution. The fourth explanation has a different character because it requires no unusual alien behavior and no unusual physics. It only requires that technological civilizations are as fragile as the historical record of the one we can observe suggests. The self-destruction hypothesis says that civilizations reliably fail before becoming sufficiently long-lived and expansive to be detectable. The same century that produces radio telescopes produces nuclear weapons. The same decade that produces the internet produces engineered pathogens and artificial intelligence systems whose alignment remains an unsolved technical problem. The window between capable of being detected and capable of self-annihilation is, on the human timeline, approximately 25 years, 1920 to 1945. On October 27, 1962, a Soviet submarine designated B-59 lost radio communication with Moscow during the Cuban Missile Crisis. American destroyers were detonating depth charges nearby as part of a pre-agreed signalling protocol the submarine crew had not been informed about. The officers believed nuclear war had already begun. Their rules of engagement authorized a nuclear torpedo launch, with agreement from 3 senior officers. 2 agreed. The third, Vasily Arkhipov, refused. The launch did not happen. The self-destruction hypothesis does not require alien civilizations to be especially reckless or unlucky. It requires them to be approximately as precarious as this one demonstrably was in the autumn of 1962. The structural problem with self-destruction is the same one that undermines every other explanation. The mechanism must work with near-total consistency. If even 5% of civilizations navigate through their dangerous transition and go on to expand for millions of years, those survivors eventually dominate the observable features of the galaxy. One long-lived, expansive civilization that made it through would leave marks impossible to miss. The filter has to catch nearly everything, nearly every time, and that requirement, that near-total consistency of civilizational failure across all of galactic history, points toward a more fundamental structural explanation. There is also a fifth explanation that sounds reasonable and fails quietly. Sometimes called the early bird argument, it suggests we may simply be among the first technological civilizations in the galaxy. The galaxy has only recently developed the heavy element chemistry necessary for rocky worlds and complex biology, and civilizations capable of broadcasting have not had time to accumulate. The problem is arithmetic. Old Sun-like stars in the Milky Way are approximately 10 billion years old. Analysis of these stars has found planetary architectures that could support life. A planet forming around a 10 billion-year-old star and following a biological timeline similar to Earth's would have produced a technological civilization roughly 5 to 6 billion years ago. 5 billion years is more than enough time to colonize the galaxy and still have 4 billion years remaining before our own civilization appeared. We're not early. We are, by any reasonable reading of the stellar timescale, among the late arrivals. If you found yourself watching this late because these questions won't leave you alone, subscribe and share this with someone who understands why they won't. That is how this channel grows. There is one more explanation worth naming before moving forward, because it is the most recent and the one that has attracted the most attention in science fiction, while being taken seriously in physics. It is called the dark forest hypothesis, named after a metaphor used by the Chinese science fiction writer Liu Cixin. The argument runs as follows. Every civilization in the galaxy knows that resources are finite. Every civilization also knows that the intentions of another civilization cannot be verified across interstellar distances. You cannot know whether they are peaceful or predatory. You cannot know what they will want when they arrive. Given these conditions, the rational strategy for any civilization that has considered the problem carefully is silence, and, if necessary, preemptive elimination of any civilization that reveals its location. The galaxy is a dark forest in which every hunter moves silently and shoots anything that makes noise. The silence is self-preservation. The dark forest hypothesis is logically coherent as a game-theoretic structure. It has several problems as a factual explanation. It requires that every civilization across billions of years of galactic history has independently arrived at this paranoid equilibrium and maintained it without exception. It requires that resource scarcity drives interstellar conflict for civilizations capable of stellar engineering, which have access to the effectively unlimited energy output of their own stars and the material resources of their own planetary systems. It requires that competition is consistently preferable to cooperation, trade, or mutual non-interference even at interstellar scales. And it predicts a specific observable pattern. Civilizations that do make themselves visible should subsequently go silent or disappear as they are eliminated. We have no confirmed instances of that pattern. The hypothesis cannot be easily falsified, and it cannot be easily confirmed. Like the zoo hypothesis, it is shaped like an explanation without providing one. Every explanation closes one door and opens one that is darker. The catalogue of answers has not produced resolution. It has produced in each failure a harder version of the same problem. And when you follow the logic of all these collapsed explanations to their common implication, one framework keeps emerging, not comfortably, but with the persistence of something the evidence keeps demanding. Before arriving at that framework, there is one more category of explanation that deserves its own paragraph, because it is the one that sounds most scientific while actually being the most optimistic. It is called the timing argument, and it proposes that the silence is not a puzzle at all, but simply an expected feature of being an early civilization in a young galaxy. On this view, complex life is rare not because the conditions are unusual, but because there has not been enough time yet. The process of producing intelligence from chemistry takes several billion years. Most of the galaxy's stars that could support life are not yet old enough to have done so. We are among the first wave of civilizations to appear, and the galaxy will become loud in another billion years as younger star systems complete the same biological sequence we did. The arithmetic destroys this explanation. The Milky Way is 13.6 billion years old. Stars old enough to have produced Earth-like timescales of biological development have existed for at least 10 billion years. a planet forming around a 10 billion-year-old star and following a biological clock similar to Earth's, would have produced a technological civilization approximately 5 to 6 billion years ago. That is not early. That is 5 billion years of lead time over us. 5 billion years is older than our Sun. The timing argument requires the galaxy to be so young that no star system has yet completed the sequence from formation to technological civilization, a requirement the age of the universe flatly contradicts. The compounding barrier version of the problem is worth laying out explicitly because it is the most rigorous formulation and the hardest to argue away. For a civilization to become galactically visible and persistent, it must not only arise, it must clear each of the following hurdles independently and in sequence. It must develop the chemistry of self-replication. It must transition to complex cellular life. It must produce multicellular organisms. It must evolve intelligence. It must develop technology. It must survive its dangerous technological adolescence. It must become sufficiently long-lived to expand physically into the galaxy. Each hurdle has a probability of success less than 1. The combined probability is the product of all individual probabilities. If even a few of those individual probabilities are very small, the combined probability approaches 0, even though each individual step seems plausible in isolation. This is why the great filter does not need a single, dramatically unlikely event to explain the silence. It needs a chain of steps where the combined probability is low enough to produce approximately 0 galactically visible civilizations in a galaxy of 400 billion stars across 13 billion years of history. The filter does not need to be one catastrophic wall. It can be a series of narrow gates, each individually passable with effort, that in combination produce an output indistinguishable from a single impassable barrier. The distinction matters because it affects what we should be looking for. If the filter is a single wall, we might hope to identify it and work around it. If the filter is a series of gates, each of which reduces the probability of making it to the next one, then every gate we can identify and understand is one whose probability we might be able to improve. The civilizational safety literature, which has grown significantly in the last decade as researchers at institutions, including the Future of Humanity Institute at Oxford, the Centre for Human-Compatible Artificial Intelligence at Berkeley, and the Global Catastrophic Risk Institute have worked on quantifying and mitigating existential risks, takes the future filter hypothesis seriously without calling it by that name. The literature on artificial intelligence alignment, on biosecurity, on nuclear risk reduction, on climate stabilization, is in a specific sense a literature about which gates in the compounding barrier stack are most likely to be the ones where civilizations fail. Identifying those gates and engineering better passage through them is, in the language of the Fermi paradox, an attempt to distinguish ourselves from the statistical pattern that the silence implies. The silence does not make this effort hopeless, it makes it urgent. This is why the great filter does not need a single dramatically unlikely event to explain the silence. It needs a chain of steps where the combined probability is low enough to produce approximately 0 galactically visible civilizations in a galaxy of 400 billion stars across 13 billion years of history. The filter does not need to be one catastrophic wall. It can be a series of narrow gates, each individually passable with effort, that in combination produce an output indistinguishable from a single impassable barrier. There is one framework that keeps surviving every attempt to dismiss it. It was laid out formally in 1998 by the economist Robin Hanson, in a paper whose title asks the most uncomfortable question in this subject: the great filter. Are we almost past it? The argument builds carefully. The path from a planet with the right chemistry to a technological civilization. Broadcasting detectable signals requires a sequence of transitions. Chemistry must produce self-replicating molecules capable of Darwinian evolution. Those molecules must give rise to cells. Those cells must develop metabolic complexity. Simple cells must transition to complex cells with internal architecture. Complex cells must organize into multicellular organisms. Those organisms must develop nervous systems capable of sophisticated adaptive behavior. Those nervous systems must produce intelligence, language, culture, and technology. That technology must reach the level of radio astronomy and spaceflight. Each transition is a step. Each step is a potential filter, a point where most candidate lineages fail to advance. This silence is evidence that at least one of these steps is nearly impossible for nearly everything. Not difficult, nearly impossible. The galaxy is old enough and large enough that even very low probabilities should have produced many visible civilizations. The absence of those civilizations in our data tells us there is a filter of extraordinary power somewhere in the chain. The filter is not a hypothesis. It is what the mathematics and the silence together force us to accept. The question is where in the chain it sits. There is a way of thinking about the filter that makes its implications more concrete. Imagine you are a scientist in the year 4 billion BCE, sitting on an inhabited world orbiting one of the older stars in the Milky Way, and you are asking Fermi's question. The galaxy at that point is 9 billion years old. Life has had 9 billion years to arise and develop. The conditions for habitable worlds have existed throughout that period. By the mathematics of the Drake equation, the galaxy should already be obviously populated. And yet, from that hypothetical vantage point, the same silence would greet your telescopes that greets ours. If the filter has been operating for the full history of the galaxy, erasing the consequences of civilizations as quickly as they arise, then the silence at any point in galactic history would look exactly like the silence we observe. The filter is not a recent phenomenon. It is a persistent feature of the galaxy's dynamics. Whatever it is, it has been preventing civilizations from becoming permanently visible for as long as the galaxy has been capable of producing them. The eukaryotic cell transition deserves more attention than it typically receives in public discussions of the Great Filter. It is the step that most strongly suggests a past filter scenario because it has a specific and unusual character. It appears to have happened only once on Earth, despite 1.7 billion years of opportunity. Every eukaryotic organism on Earth, every plant, animal, fungus, alga, and protist, traces its ancestry to a single ancestral eukaryote. This ancestor appears to have arisen from a specific merger between two types of prokaryote, in which one was permanently incorporated into the other as the mitochondrion. The merger appears to have been an event that happened once in the history of life on Earth, and then propagated into all subsequent complex life. If this event required conditions so specific that it occurred only once in nearly 2 billion years of microbial life on a planet with a liquid ocean covering most of its surface, then the galaxy's inhabited worlds may be overwhelmingly microbial. Bacterial ecosystems on every ocean world, bacterial chemistry on every habitable surface, and nowhere, except by extraordinary accident, anything more. The origin of life transition and the eukaryotic transition are not the only past filter candidates. There is also the transition to multicellularity, which in fact occurred multiple times independently on Earth, in animals, plants, fungi, and several lineages of algae, suggesting it is not the bottleneck. There is the development of sexual reproduction, which dramatically accelerates the pace of evolutionary innovation by allowing advantageous mutations to combine across lineages. There is the transition to land. There is the development of powered flight. There is the development of large brains. Most of these transitions appear to have occurred more than once on Earth, which suggests they are convergent and not the bottleneck. The eukaryotic cell and the origin of life stand apart precisely because they appear to have happened only once, in contrast to the many other evolutionary transitions that recurred independently. The implication for the search is specific. If the bottleneck is in the biological past, the most informative discovery would be finding life on Mars or in the subsurface oceans of the outer solar system that is genetically or biochemically unrelated to life on Earth. This would tell us that the origin of life is not the filter, because it happened independently at least twice in one solar system. It would push the filter toward either the eukaryotic transition or a later step. If the Martian life we found was genetically related to Earth life, that would suggest panspermia rather than independent origin, and would not resolve the question. The distinction matters. It is why Mars sample return is, in the context of the Fermi paradox, one of the most important scientific missions ever planned. If the filter is behind us, we are the miracle. If it is ahead, we are next. If the filter lies in the past, we have already crossed it. The most widely discussed past filter candidates are the origin of life and the development of the eukaryotic cell. The origin of life is the step least understood even on Earth. We know the chemistry is available. The Miller-Urey experiment in 1953 demonstrated that amino acids form spontaneously from simple gases and electrical sparks within days, and subsequent experiments have produced nucleotides, fatty acids, and other molecular building blocks of life under conditions plausible for early Earth. But there is a profound gap between having the building blocks and having a genuinely self-replicating system capable of Darwinian selection. We do not know how that gap was crossed on Earth. We have candidate scenarios, including the RNA world hypothesis, which proposes that RNA molecules capable of both carrying genetic information and catalyzing chemical reactions preceded both DNA and proteins. We do not have a confirmed mechanism. If crossing that gap requires a molecular accident with a probability something like 1 in 10 to the power of 40, then even a galaxy full of Earth-like planets produces life almost nowhere. The silence is explained. We got through. The worst is behind us. The eukaryotic cell is the other major candidate. All complex life on Earth, every plant, animal and fungus, is built from cells with a membrane-bound nucleus and internal organelles. The transition from simple prokaryotes to eukaryotes took approximately 1.7 billion years after life first appeared on Earth, and appears to have involved a single specific symbiotic merger. One bacterium was engulfed by another and retained as what eventually became the mitochondrion. Every mitochondrion in every eukaryotic cell on Earth traces its ancestry to this one event. If that merger required conditions so specific that it happened only once in 1.7 billion years of bacterial life on one planet, the galaxy may be full of inhabited worlds that have never gotten past the microbial stage. Intelligence and complexity would be the accident, not the rule. The universe does not need you to rush through this. Now consider the other scenario. What if the steps behind us are not the hard ones? What if the origin of life is straightforward, occurring readily wherever conditions allow? Organic chemistry is common throughout the universe, found in meteorites and interstellar gas clouds. What if multicellular complexity follows naturally from eukaryotic cells given enough time? What if intelligence is a convergent outcome that evolution tends toward whenever certain conditions are met? If all of that is true, the filter is not in the biological past. It is somewhere in the technological present or near future. It is a challenge that civilizations encounter at or near the level of development we have currently reached, and that they consistently fail to navigate. Not because the universe is malicious. Because the capabilities that make a civilization detectable, nuclear physics, synthetic biology, computing power, artificial intelligence, are the same capabilities that create the risks that end it. Consider the specific timing of what we have built. Humanity became electromagnetically detectable around 1920. By 1945, we had nuclear weapons capable of ending complex civilization in a large enough exchange. By the 1980s, we had enough warheads deployed on both sides of the Cold War to produce nuclear winter conditions severe enough to collapse global agriculture. The gap between detectable and self-destructive was approximately 25 years. If that gap is representative of what happens to technological civilizations in general, the population of civilizations that are detectable and still intact at any given moment would be very small. But the future filter argument is more uncomfortable than just nuclear weapons. We are now developing artificial intelligence systems of rapidly increasing capability whose alignment with human values remains an unsolved technical and philosophical problem. We are navigating climate disruption in real time. We are building synthetic biology tools with a dual-use character that makes the creation of dangerous pathogens by small groups increasingly accessible. None of these are speculative risks for a civilization at our level of development. They are present tense realities. The future filter does not need to be exotic. It needs to be whatever civilizations consistently fail to manage at approximately the level we have reached. The most unsettling version of this argument does not require specifying a mechanism at all. It simply observes that the silence is consistent with the hypothesis that civilizations consistently fail at our stage. The galaxy keeps the answer in the form of absence, which is the only form the answer can take from the outside. The civilizations that could tell us what ended them are not available to tell us. Now consider the implication that changes the weight of future discoveries. If we find microbial life on Mars, or chemical biosignatures in the plumes of Enceladus, or oxygen-methane combinations in an exoplanet atmosphere that can only be produced biologically, that discovery would be one of the most celebrated in the history of science. It would also shift the filter's probable location. Finding life elsewhere in our solar system would tell us that the origin of life is not the bottleneck. Life arises wherever conditions allow. The filter would then be somewhere later in the chain, closer to where we currently stand. The warmly celebrated discovery that we are not alone would contain, embedded in its implications, a tightening of the probability that the thing which ends civilizations is ahead of us, rather than behind. The joyful scientific discovery of the century would simultaneously be a warning. There is a way to hold this that does not require the Great Filter to be a single catastrophic event. The filter might not be one thing that ends civilizations in a sudden collapse. It might be a combination of pressures that gradually reduce the probability of long-term survival without any single decisive failure. A civilization navigating nuclear risk and succeeding, then navigating engineered pathogens and succeeding, then navigating climate disruption and succeeding, then encountering a risk that has no precedent in its history, perhaps arising from artificial intelligence systems operating beyond the comprehension of the biological minds that created them, or from some other technological development with no analogue in our current experience. Each individual challenge survivable, the combination across centuries progressively reducing the expected lifespan of technological civilizations to something short enough that none of them leave a permanent mark. This version of the filter is more difficult to dismiss than a single mechanism scenario, because it does not require any single unprecedented catastrophe. It only requires that the challenges accumulating at our level of technological development are, in aggregate, harder to navigate than they appear from the inside. From the inside, each challenge looks manageable. From the outside, the statistical result of how civilizations manage them is written in the silence. Enrico Fermi was famous among his colleagues for a method of reasoning called Fermi estimation, making accurate order of magnitude calculations from first principles, using only rough knowledge and careful logic. The piano tuners in Chicago, the number of gas stations in the United States. He would pose these questions at lunch and work through them on a napkin, arriving at answers within a factor of 2 of the correct value without looking anything up. The question he asked that afternoon in 1950 was, in its structure, a Fermi estimation problem. He was not speculating, he was calculating, and the calculation said, the galaxy should be full. The observation said, it is not. Fermi recognized the gap immediately. He did not have a name for it. He had 4 words. The gap has not closed. It has been measured more precisely in the 75 years since that lunch, and the precision has made it larger, not smaller. The more accurately we count the potentially habitable worlds, the more clearly we can describe what a colonized galaxy would look like, and the more confidently we can say that the sky does not look like that. The measurement is exact, the explanation is not. And the most important thing about a precise measurement without a satisfying explanation is that it tells you something has been missed. Something in the chain from star formation to galactic civilization is doing something the equations do not account for. The filter, real, somewhere. Its location the most important unsolved problem in science. What comes next will make sense once this has had time to land. There is a version of the Great Filter that does not require specifying any mechanism at all. It is the most austere version. The Milky Way is old. The conditions for habitable worlds are common. The silence is total. Given those 3 facts, at least one filter of extraordinary power exists somewhere in the chain from chemistry to galactic visibility. That filter is real. Its name and specific mechanism are unknown. Its effect is written in the silence. And a civilization currently at the transition point between early technology and either long-term stability or collapse is in a particular relationship to that silence that deserves to be held clearly rather than looked away from. It is worth separating what the science actually says from what the speculation around this subject sometimes implies. They are different things, and conflating them produces confusion in both directions. What the science says, we have not detected a confirmed signal from an extraterrestrial technological civilization. The WOW signal of 1977 is the single most anomalous detection in 60 years of searching, 30 times background noise, narrowband at the hydrogen line for exactly 72 seconds, and it has never been reproduced. Every other candidate detection has been attributed to natural or human-made sources. Breakthrough Liston's survey of the nearest million stars found no signals meeting criteria for further consideration. The WISE All-Sky Infrared survey found no confirmed signatures of large-scale stellar energy capture. The Kepler Transit Catalogue contains no confirmed megastructure candidates that survived follow-up analysis. The scientific record is a null result accumulated across 6 decades of increasingly capable instrumentation. We're not waiting for an answer. We have one. We're deciding whether we are brave enough to accept it. What the science does not say, it does not say we are alone. The fraction of sky, frequency space, and signal types covered by every search conducted to date remains a subset of the full possibility space. A civilization transmitting in directions that do not intersect our current observational coverage, at power levels below our detection threshold, using modalities we have not searched for, would not appear in our data. Absence of a confirmed detection is a constraint. It is not a proof, but a constraint that has been growing more precise for 60 years against a mathematical backdrop that demands signals be present, carries evidential weight that increases with each passing decade. 3 types of evidence would most substantially advance the question. A confirmed detection of extraterrestrial intelligence would tell us the galaxy is not as quiet as our searches suggest, and would require a new account of why contact took this long. The discovery of life elsewhere in our solar system, even microbial life, would rule out the origin of life as the filter and shift the probable location of the filter toward where we stand. Continued null results from increasingly thorough searches would strengthen the pass filter interpretation and suggest the bottleneck is in the early biological steps rather than in the technological ones. All three outcomes are achievable within this century. The James Webb Space Telescope is already characterizing exoplanet atmospheres at sensitivities that could detect biosignature gas combinations on nearby worlds. NASA's Europa Clipper, launched in 2024, will spend years analyzing the chemistry of Europa's ocean environment. Mars sample return missions planned for the 2030s will bring Perseverance rover's rock cores to Earth laboratories where analysis sensitivity exceeds anything that has ever operated on the Martian surface by orders of magnitude. If you're listening in the dark, let that image rest with you. The Fermi paradox is not, at its core, a question about aliens. It is a question about what kind of universe this is and what position we occupy within it. If the filter is in the past and we are the miracle, we carry an obligation that no other entity in the observable galaxy appears to carry. The obligation not to waste the extraordinary accident of our existence. If the filter is ahead, the silence is a record written in the absence of every civilization that reached this point and failed to navigate it. In either case, the question is the most important context in which decisions about our technology, our institutions, and the next century of human choices are being made. What makes this moment historically unusual is that we are the first generation with the tools to ask Fermi's question rigorously. Before radio astronomy, the question could be posed philosophically, but not searched. Before Kepler, we could not know whether other stars had planets at all. Before breakthrough, listen, we could not claim to have surveyed even the nearest million stars with serious sensitivity. All of that capability fits inside a single human lifetime. The search has barely started, and the silence it has returned, measured with increasing precision across that entire period, is the most important datum any civilization has ever produced about its position in the universe. The silence is the honest answer the universe has given so far. It does not say we are alone. It does not say we are not. It says, given every instrument we have pointed at the sky, given 60 years of careful searching, the signal we expected has not arrived. That is all it says. Depending on what you do with it, it is also the most consequential sentence any civilization has ever had to read. There is a specific thought experiment that clarifies the emotional weight of the filter question. Suppose you're standing at the edge of a swimming pool. The pool is large and it has been filled with clear water for as long as you can remember. You have never seen anyone else in the pool. You have looked carefully. The water is still. Now, two things are possible. Either the pool is genuinely empty because people are rare, and you happen to arrive before anyone else did, or the pool has a drain that periodically removes people who enter it, and everyone who came before you has already gone down the drain, and you are standing at the edge about to step in. The water looks identical in both scenarios. The silence looks identical. The question is which scenario you are in, and the answer matters enormously for whether you should step in enthusiastically or carefully, and what you should do while you're in there. Fermi's question is the question of which pool you're standing in front of, not metaphorically, not in the abstract. The observable evidence at this moment cannot distinguish between a galaxy where we are early arrivals in a pool that will eventually fill up, and a galaxy where the pool drains regularly and we are approaching its edge. The distinction requires the kind of evidence that James Webb and Europa Clipper and Mars sample return are positioned to provide. In the meantime, the honest position is that we do not know. The stakes of being wrong in one direction are very different from the stakes of being wrong in the other, and we are making decisions about our technology, our governance, and our future without knowing which pool we are standing in. The search itself is not stalled. It is accelerating in multiple directions simultaneously, using instruments more capable than anything that has existed before. The next decade of exoplanet atmospheric characterization by James Webb will produce the most comprehensive survey of planetary chemistry ever assembled. The Europa Clipper's multiple flybys of Europa will characterize the ocean environment in more detail than any prior mission. The Square Kilometre Array, a radio telescope network under construction in South Africa and Australia, will have a sensitivity far exceeding any prior radio observatory, scanning the sky for signals at power levels that would have been undetectable by every instrument operated in the 60 years of SETI history before it. The question is moving, slowly and irreversibly, from the domain of pure inference toward the domain of evidence. There is a version of the Fermi paradox that is not about the galaxy at all. It is about this century. The specific decisions made in the next 50 to 100 years about nuclear arsenals, about biosafety, about artificial intelligence governance, about climate response, will either narrow or widen the probability that humanity becomes the kind of long-lived civilization that eventually leaves a detectable mark on the galaxy. If the filter is ahead, those decisions are the filter, not in the abstract sense that they determine our long-term future, but in the precise sense that they are the class of challenges the filter is made of. The same challenges that have ended every other civilization at this stage, if the future filter hypothesis is correct, are the challenges currently appearing on human policy agendas. Nuclear arsenals that remain on hair-trigger alert decades after the Cold War that justified them. Gain-of-function research that builds capability faster than biosafety governance can track it. Artificial intelligence systems scaling faster than our understanding of their alignment properties. The Fermi paradox, understood clearly, is not an abstract question about alien civilizations. It is a precise description of the situation humanity is currently in. There is also a dimension of the Fermi paradox that rarely makes its way into public discussions, what it reveals about the civilization asking it. We are a species that can look at the sky with enough sophistication to know what should be there if the universe followed the patterns we would naively expect from the Drake equation. We can formulate the question, we can build the instruments, we can listen, we can survey. We can sit with the discomfort of a result that arrives as silence rather than signal. The capacity to hold that silence as a scientific datum rather than filling it with mythology, reassurance or denial is recent. It is not guaranteed to persist. And it is the same capacity that makes the question of the filter's location feel personal rather than merely academic. If the filter is passed and we are the miracle, we are the first entity in the observable galaxy, as far as the evidence shows, that has developed the ability to ask whether it is alone and to search rigorously for the answer. That is not a small thing. It is an extraordinary responsibility that comes with no instruction manual, because there is nothing else in the observable data that has done it before and survived long enough to be useful as a reference. If the filter is ahead, this silence is the only warning we will receive, written in the absence of everyone who reached this point before us. In either case, the question demands to be taken with the seriousness its implications deserve. There is a habit of mind that makes the future filter scenario harder to think about clearly, and it is worth naming directly. When we look at the history of technological development so far, we tend to focus on what went right. The nuclear arsenal was built, and it has not been used in warfare since 1945. Engineered pathogens have been developed in laboratories, and none have yet caused a pandemic attributed to intentional release. Climate change is accelerating, but civilization continues. The habit of mind says, we have survived every dangerous technology so far, so the pattern suggests we will continue to do so. This reasoning sounds reassuring. It is, in a specific technical sense, a form of survivorship bias, We can only reason about the history of civilizations that survived. The civilizations that did not survive are not available to contribute their perspective. If the future filter is real, the civilizations currently at our stage of development feel exactly as we feel right now, which is to say, cautiously optimistic, having survived the dangers visible to them so far. They feel this way right until they don't. The astronomer Robin Hanson, who formalized the Great Filter argument, has pointed out that the filter's location has a specific emotional valence. If we discover strong evidence that the filter is in the past, that the origin of life is extraordinarily improbable, or the eukaryotic transition nearly impossible, that is good news. It means the worst is behind us. Our future is, in principle, open. We should feel relief. If we discover strong evidence that the filter is ahead, as finding life on Mars would suggest, that is bad news in the specific sense that it narrows the probability that we survive our technological adolescence to become a long-lived, visible civilization. The evidence that we are not alone would simultaneously be the evidence that alone is what we are likely to end up. This is a strange kind of scientific result. Most discoveries are celebrated without this ambiguity. Finding life on Mars would be one of the great scientific moments in human history. Every newspaper in the world would carry it as the lead story. Every government would issue a statement. The implications for our understanding of the universe would be immediate and profound. And yet embedded within that discovery, visible only to those who know where to look, would be a tightening of the probability on a future that ends quietly, without broadcasting a final signal, without leaving a mark visible from other star systems, without ever knowing what ended us. The detection of life elsewhere in our solar system would contain both of those things simultaneously. The joy and the warning, packaged together, available only to a civilization careful enough to look at both at once. There is a useful way to think about the two scenarios that makes the distinction concrete. Suppose the filter is in the biological past. The origin of life is extraordinarily improbable, occurring perhaps once in every 10 to the power of 30 habitable planets per billion years. In that case, Earth is a statistical outlier of a magnitude so extreme that it should not have happened. Our existence is the result of the universe running a lottery with nearly impossible odds an enormous number of times. We won. No one else did. The silence is the sound of a nearly empty lottery, with us as the one ticket that came up. In this scenario, the universe is full of planets with the right chemistry that are simply waiting, in silence, for a probability that will almost certainly never arrive. We are the accident that happened once. Now suppose the filter is in the technological future. Civilizations arise at a rate consistent with what the Drake equation's optimistic input suggest, but they consistently fail to survive their transition through advanced technology. In that case, Earth's history up to this point is not unusual. Life arose, it developed complexity, it produced intelligence. All of this happened because these steps are relatively likely given the right conditions. What is unusual is not that we exist, but that we are still here at the specific moment in our development when the dangerous capabilities are being built. In this scenario, the universe is full of planets that got to where we are and then went quiet. The silence is the sound of a graveyard, and we're standing at its edge, looking in, not yet understanding what ended the ones who came before. There is a lunch table at Los Alamos that no longer exists. The building is still there. The physicists who sat at it are not. But the question one of them asked at that table in 1950 is still open. Where is everybody? Fermi asked it, with the quiet confidence of a man who had run the numbers in his head and found them unsatisfying. 4 words. The answer, 75 years later, is not 4 words. It may be the hardest question in science. What has changed since that lunch table is not the question. The question is identical. What has changed is the weight of what now stands behind it. In 1950, we had 0 confirmed exoplanets. We had no images of any world other than our own. We had no data from Mars, no plume detections from Enceladus, no atmospheric spectra of worlds around distant stars. We could not know the galaxy was crowded with potentially habitable worlds at the density the numbers now suggest. The math has gotten more precise. The searches have grown more capable. The silence has remained. Accumulated across 6 decades and measured with progressively more sensitive instruments, the silence is no longer a shrug. It is a measurement. And the measurement says, the galaxy is old enough and large enough to have produced many civilizations before us. The colonization timescales say, those civilizations should have left marks we cannot miss. The marks are not there. Something in the chain from chemistry to civilization acts as a filter of extraordinary power. The filter is real. Its location is the question with the most direct implications for the civilization currently asking it. What makes this version of the question different from every other scientific question humanity has ever faced is that the answer changes what we should do right now. Most scientific questions are interesting without being urgent. The answer to whether dark matter is composed of axions or WIMPs does not affect how you should manage nuclear arsenals or artificial intelligence development or pandemic prevention. The Fermi paradox is different. If the filter is in the past, we are extraordinarily lucky outliers in a galaxy that rarely produces anything like us, and our survival and expansion matter in a way that nothing else in the observable galaxy currently matches. If the filter is ahead, the class of challenges that has ended every civilization before us is the class of challenges currently appearing on human policy agendas. In either case, what we do with this century is not a question that can be separated from the question Fermi asked. They are the same question, viewed from different angles. There is one more dimension of the search that rarely appears in popular discussions and deserves its own paragraph. The search for extraterrestrial intelligence is not only a scientific program, it is a philosophical commitment to the idea that questions that seem unanswerable might, with sufficient ingenuity and patience, become answerable. In 1950, the idea of searching for signals from other civilizations was treated by most of the scientific community as science fiction. By 1960, Frank Drake had built an instrument to do it. By 1995, we had confirmed that other stars have planets. By 2022, we had instruments characterizing the atmospheric chemistry of those planets. The scientific infrastructure required to give the Fermi paradox a rigorous empirical answer did not exist in 1950 and is being built in the lifetimes of people who were alive when Fermi asked the question. The search has not failed. It has barely started. What it has produced in its brief history is a silence that the mathematics did not predict and that the instruments cannot yet explain away. That is not a failure. That is a discovery waiting to be characterized. The 4 words Fermi asked in 1950 are doing more scientific work now than they were then. Every exoplanet confirmed by Kepler adds to the denominator of the Fermi calculation. Every null result from Breakthrough Listen tightens the constraint on what kinds of signals at what power levels are absent in what fraction of the sky. Every infrared survey that finds no megastructure candidates narrows the parameter space available to the filter's defenders. Every Mars sample and every Europa flyby tightens the probability distribution on where in the biological sequence the bottleneck lies. The question is not static. It is being answered, piece by piece, by the most capable instruments humanity has ever built, pointed at the most important question humanity has ever asked. The silence measured with increasing precision every year, continues to be the most significant datum any civilization has ever produced about its position in the universe. Where is everybody? That is still the question. After 75 years of looking, it is still the right one. You're sitting inside that chain right now. Not as a spectator watching from the outside, as one of the data points. If this is the kind of thinking you want more of, subscribe and share this with someone who asks the same questions in the dark. That is how this channel grows. Fermi went back to his food. The conversation at the table moved on. The question he put into the room that afternoon, 4 words, has not moved at all. It has been sitting in the silence ever since, waiting for an answer that has not yet arrived. That answer, when it comes, will be the most important thing any instrument has ever returned. And it will be written, one way or another, in the silence or the breaking of it. This silence is the answer